Welcome to the fifth module of the ESCSI series on internal curing. And in this fifth module, we're going to focus in on how internal curing can be used to improve the sustainability of concrete. Let's begin by discussing the fact that the concrete industry has become much more aware of how important sustainability is. Specifically, the concrete industry is really looking at ways to minimize the environmental impact of concrete construction. As a part of this, in this module, we are going to discuss ways that internal curing can be used to produce more sustainable concrete designs. Specifically, we're going to focus in on two approaches. The first is to understand how the service life of concrete can be improved by using internal curing. Specifically, we'll focus on how internal curing can reduce the potential for corrosion in reinforced concrete systems. Second, we'll understand how internal curing can be used with supplemental materials to reduce the amount of cement or clinker inside of our concrete, thereby reducing the carbon footprint. As we've mentioned, the concrete construction industry is becoming actively aware of the need to develop more sustainable concrete solutions. And internal curing provides one method that can be used with a three-pronged approach to making concrete more sustainable. Specifically, we're going to focus in on improving the service life while reducing the clinker and the cement content in the overall system. Let's begin our discussion with the improved service life of concrete. Now, as we've seen in the earlier modules, internal curing has the potential to provide additional water that will hydrate more of the cement and hydrate more of the supplementary cementitious materials that are in our system. By hydrating more of those materials, we have the potential to reduce porosity and reduce the connectedness of the interfacial transition zones. And this is very beneficial in the fact that it can reduce the transport properties of concrete. When we discuss transport properties, we're really discussing how the concrete absorbs water or absorbs solutions that contain chloride ions or other ionic species, or how these ionic species diffuse through the concrete and get toward the reinforcing bar. So internal curing, by hydrating more of the cement, reducing the porosity and reducing the connectedness of the interfacial transition zones, is going to reduce the speed at which the chloride ions can get to the reinforcing bar. By reducing that speed that the ions are going to move through our concrete, we can extend the time that our concrete will be in service before the corrosion starts at the bar. In addition to this, however, internal curing has the major benefit of reducing the potential for shrinkage cracks. And these are the cracks that can develop in the system and provide a short circuit for those chloride ions to get to the bar. So we really see that internal curing is going to work primarily in two ways in terms of improving the overall service life. One, we're going to be able to get more out of the matrix itself because we've reduced the porosity and reduced the connectedness of the interfacial transition zones. But much more importantly, we're going to minimize the potential for cracking. And by reducing that potential for cracking, we're taking out these short circuits that can get the chloride ions right to the reinforcing steel. Now we can begin here with a very quick model that will discuss several of the different bridge decks that we've seen earlier in these modules. What we're really looking at here are four different concretes that have been tested. The first two concretes were tested in Monroe County in Indiana. The second two concretes are the ones that are coming from the studies by the New York Department of Transportation. The first thing that we can notice when we look at the internally cured concretes in a conventional system are that we would have about 20 years before the concrete begins to go into corrosion. Now, one of the interesting components of this is this model that we're using here assumes that the concrete is completely uncracked. So we can see a slight benefit when we use internal curing going from maybe 18 to 22 years, but we're really not accounting for the major benefit of reducing the overall cracking in the concrete system. Those cracks would reduce the time of corrosion for the blue line to a much shorter time because the chloride ions are able to get right to the reinforcing steel. So the first thing that we can see, again, the internal curing allows us to have improved transport properties in our concrete, which will slightly extend the time to corrosion. What's more important probably in this whole discussion is that we can start to begin to use higher performance concretes which are more prone to cracking, which would take us to what we're seeing in the New York Department of Transportation mixtures, shown here as the green line, which is concrete out of a bridge deck in Lisle, New York, and the black line, which is concrete from the Tonawanda bridge decks in New York. And what we can see is by moving from a conventional concrete, which was shown in that blue line, to a higher performance concrete with a lower water to cement ratio and the addition of supplementary materials, we can start to extend the time to corrosion from 20 to, let's say, 55 to 80 or so years. And by using internal curing, we can dramatically reduce the potential for cracking, which is really the Achilles heel of these high-performance concrete mixtures. Now, a life cycle model was developed by Cusson where he incorporated the effects of both the improved diffusion coefficients of our concrete with internal curing, and he accounted for the improvements by removing reducing the potential for cracking. So Cusson's study really examined a conventional concrete, a high-performance concrete, and a high-performance internally cured concrete with an 8-inch thick bridge deck with 3 inches of cover that was exposed to a Canadian environment. Now, in this service life model, as previously described, Cusson began to discuss both the impact of the chloride ion diffusion in the system, but also the potential benefits of reducing cracking. And by reducing chloride diffusion and reducing cracking, you're able to extend the time till you see all of the degradation that's taking place with the stress generation by the bars and the damage that's taking place due to cracking caused by the corrosion in the overall system. Now, one of the main takeaways from this study can be seen in this bar chart. If we look at the comparison of conventional concrete to high-performance concretes, we can again see the same type of benefit that we saw when we compared the Monroe County bridge deck to the bridge decks from New York, where we can see that the service life would move from approximately 22 years to approximately 40 years for the going from a conventional to a high-performance concrete. However, we can see an even bigger improvement when we start to look at going to a high-performance concrete that's been internally cured. The main benefit here is that by internal curing our concrete, we're reducing those cracks and we're reducing the potential for corrosion at those cracks and really seeing a dramatic improvement in service life. Now, in addition to what we've just discussed on improving the service life by extending the time to corrosion, internal curing has the potential to reduce cement content and reduce the clinker that's being used in concrete. And by doing this, we have the potential to really reduce our carbon footprint. Now, the first question may be, where does this carbon footprint come from? And a large portion of the carbon footprint has to do with cement production. Cement production produces carbon dioxide, and this carbon dioxide is going to come from three main sources. It's going to come from the calcination in the system, which is going to be about 50% of the CO2 that's produced. It's going to come from the combustion that's occurring inside of the kiln and the fuel that's being used there, which will be about 40% of the CO2 that's produced. And then the transportation to get the cement and concrete to site. While concrete itself has a relatively low carbon emission per unit volume, we use such an enormous volume of concrete that this is really what accounts for such a high amount of CO2 when it's used in the world. So one of the things that the concrete industry has really tried to do is it's tried to figure out, are there ways that we could reduce the amount of cement or clinker that's being used in the construction of different structures? And many people have asked, can we start to use supplementary materials, for example, to replace a portion of this clinker? These supplementary materials may be fly ash, they may be slag, they may be replacing a portion of the clinker with limestone, for example. And the real question here is, can we start to do this? And if we start to try to do this, what are some of the potential limitations that we can have? Now, one of the limitations can be slower hydration or slower set time, slower strength development. And the other limitation can really be sort of classified as the need to provide longer curing times for these mixtures. And both of these really speak to the fact that the supplementary materials may not be as reactive as the cement, and they may require us to do things in addition at early ages. And those things we think can be addressed in a couple different ways. The first way that we're going to start to address these with internal curing is we're really going to start to look at, can we change the overall mix design of our system? And an example of this has been recently published by De La Varga. De La Varga has really examined how higher volumes of fly ash might be able to be used if we start to look at the entire concrete system and we start to look at the overall mixture design process. So here, what we're going to be doing is comparing a conventional concrete bridge deck mix with a water to cement ratio of 0.42 to see what we might be able to obtain if we go to a higher volume fly ash mixture, where maybe in addition to just replacing some of the cement, we alter the water to cement ratio of the system. Now, I think it's important that we're going to note here, during the portion of this study, we've kept a similar amount of paste in the system, irrespective of the amount of fly ash that's being used. So the paste in the system is constant, the aggregate volume of the system is constant, and what we're really doing is replacing a portion of the cement with fly ash. By replacing that portion of the cement or clinker, we're essentially removing that portion of the CO2 that's associated with that portion of the concrete that's being constructed. Second, we're going to maintain similar workability, and this is going to be coming from adjusting our water reducers inside of the overall system. So we're going to look at a system where we're going to replace 20, 40, 60, or 80% of the cement by volume. And in addition to just replacing the cement, what we're going to do is we're going to look at altering our water to cement ratio. So we're going to move from a 0.42 water to cement ratio in our conventional design to a 0.36 or maybe even a 0.30 water to cement ratio. Now, in doing this, the whole idea is that we may be able to overcome some of the limitations that people have seen with slower strength development at early ages or lower overall strength development when we replace some of the cement or some of the clinker. So to really start to take a look at this, we can start to look at the early age compressive strength when we start to alter our water to cement ratio. So our 0.42 reference mixture is shown here in blue. And what we can see is that we'll go from a compressive strength of about 20 MPa at 1 day up to about 35 or 37 MPa at 7 days. And if we were to just reduce the water to cement ratio of our system, we go from a 0.42 to a 0.30, we can see ourselves shifting from that blue line up to that red line, where we're seeing a substantial improvement in strength. We might be doubling the strength at the first day. We might be going from about 35 MPa up to about 60 MPa at 7 days. So just altering the water to cement ratio does exactly what we would have expected it to do, reduces our porosity and increases our strength. However, this is where we may be able to take advantage of those improvements in strength in a way that we can actually make our concrete mixtures more sustainable. Here what we're going to do is we're going to use a lower water to cement ratio. However, we're going to replace a large portion of the cement with a supplementary material like fly ash in this particular case. So replacing 40% of the cement resulted in the green line that you can see, and replacing 60% of the cement resulted in the black line that we see on these mixtures. So one of the big takeaways that we can see is that if we replace some of the cement with fly ash and we alter our water to cement ratio at the same time, we can still get very similar early age strengths in these systems, which would be very important when it comes to early strength for formwork, early strength for using that structure at early ages. And this is obtained by not only just replacing the cement, but by also altering our water to cement ratio. In addition, by altering our water to cement ratio, we're able to greatly improve our transport properties because, as we know, as we reduce the water to cement ratio, we're going to cut down on fluid flow in those systems. However, as we've seen in our previous modules, reducing the water to cement ratio is going to increase the autogenous shrinkage, and it's going to increase the potential for cracking. So this is really where you can start to see where the benefits of internal curing are going to be in this system. By using a lower water to cement ratio, we're able to replace a larger proportion of the cement. When we replace a larger proportion of the cement with fly ash, we need to supply additional curing water, and we need to supply internal curing to these systems to reduce the potential for autogenous shrinkage and cracking. So let's see what happens when we start adding internal curing to these systems. Now, the open symbols are going to be our internally cured mixtures, and the real takeaway from this is internal curing has the ability to provide us very similar, if not slightly higher strengths than what we see in our conventional systems. So we're providing a system that now is going to provide more water to hydrate the fly ash, more water to hydrate slag, but providing an overall similar compressive strength to what we see in our conventional system. In addition, by supplying the internal curing water, we can dramatically reduce the potential for shrinkage and cracking. Another way that we can look at this is we can essentially start to look at comparing that conventional mixture that we saw with these lower water to cement ratio mixtures where a high volume of cement has been replaced with fly ash. And we can see here pretty dramatically in the graph at the center, which was taken after 28 days of curing, and the graph on the right-hand side, which was taken after 90 days of curing, that by moving from a 0.42 water to cement ratio, which is the blue line, to our 0.3 water to cement ratio, either pure cement, which is the red, or cement where 40% of the cement has been replaced by fly ash, or 60% of the cement has been replaced by fly ash, as we see with the dark line, we see a substantial reduction in fluid transport. We see in all of those cases, whether it's a straight cement system or whether 40 or 60% of the cement has been replaced, the water absorption is substantially lower than what we saw in our reference conventional bridge deck concrete mixture. This really talks to the benefits of internal curing. In addition, these internally cured mixtures had the same cracking potential that we saw in the conventional 0.42 water to cement ratio mixture. So this is really a big benefit. By using a lower water to cement ratio, we're able to overcome some of the early strength limitations. We're able to improve our transport properties, and we're able to reduce the risk of cracking in those mixtures. So in summary, what we've seen in this module is that internal curing works by increasing the hydration of the cement and supplementary materials. It's going to allow us to use our binder more efficiently, which means that this is going to be working very well when we start to talk about supplementary materials or Portland limestone cements. Internal curing is going to provide us the ability to reduce the potential for cracking, and this is going to be very important in the systems as well. We're going to be able to reduce chloride ingress in those systems because we've hydrated more of the system and we've disconnected more of the connected interfacial transition zones. The impact on sustainability really comes in two main ways. First, service life models were used to show an improvement in service life in two main ways. The first is by moving from a conventional concrete to a higher performance concrete, we're able to get a substantial improvement in the overall service life. Second, we're able to see benefit by having additional internal curing water and hydrating more of the cement and making it harder for the chlorides to get to the reinforcing bar. Finally, by reducing the cracks in the system, we can dramatically extend the time until the reinforcing bar starts to corrode. In doing this, we saw substantial improvements in the service life of our structures, which leads to a substantial impact on the sustainability. Second, when we use internal curing with supplementary materials, we're able to reduce a larger portion of the clinker or the conventional cement that's inside of our concrete. Now, this is going to really allow us two main benefits when we start to talk about internal curing. First, we're providing additional water in that system, and that additional water can be useful because our supplementary materials are going to react more slowly. Second, we're able to reduce the potential for cracking, which allows us to adjust our water to cement ratio in a way that's going to allow us to counteract some slow strength development and improve our overall transport properties. So hopefully you found this module to be useful as we talk about how internal curing can be used to improve the service life and to improve the carbon footprint of our concrete mixtures. If you'd like more information on the subject, there are several different references that are attached here, as well as different references on the ESCSI website, which is also listed. We'd like to thank you for tuning in to the 5th module in the ESCSI series on internal curing.